Hey guys, welcome back to another part of the neural networks tutorial. Not tutorial, but series where we're going to be building a neural network from scratch in JavaScript. So far in the previous two parts we've created a network, and we've also added persistence, which basically lets us persist the network's weights and biases over different reloads, which is going to be crucial because now it's going to let us improve our network and save the results. So in this part I'm actually going to be adding the learning algorithm, which is the main part, and like how the network actually learns and improves so that it can accurately predict things. So I'm going to be showing you guys how it works, and I'm going to be using a method called a finite gradient or finite gradient descent, which is what I actually call it. I don't know if that's actually the real term, but I'll show you what it is later. But the first thing I'm going to do is organize our script. So right now just have it's kind of all in one file and it's a bit messy, so I'm actually going to organize it a little bit. Just going to add one more called network.ts, and we will move all of the network stuff into there, like this, and we'll also have to copy in something like this. Alright, so now I can actually start. So let me open up Klecky Paint tool again, which is what I've been using to demonstrate. Let's just create the basic neural network, which we have functioning over here. So we got the two input neurons, 3 hidden neurons, and then 2 output neurons again. And let's create the weights. So this weight, the weight from this neuron, they're going to connect to every other neuron like this. Same for this one, like that. I'm not going to draw those in. And then same for this one, they connect to every neuron in the next layer like that. And of course these all do the same thing, but I'm not going to draw all of those in because then our diagram looks a bit messy. So there we go. Anyways, in this part we actually want to increase or decrease increase this network's accuracy. So the first thing that we're going to want to do is actually get a measure of how good the network currently is. So I'm going to go down here and create some space, and I'm actually going to create a new function. Let's say we input the items or values 5, 3, we're expecting output 1, 0, but instead we actually get something like 0.5, oh that's really bad, and we get 0.4 here. So these are real values which we want, these are our actual values, and we can actually measure network's accuracy by subtracting these like this and squaring them, then adding them all up, which gives us an overall cost, which is the term we use to define a network's accuracy. The cost of this is going to be 0.5 squared plus 0.6 squared, which I believe is 0.61, although I'll have to check that. 0.5 squared is 0.25, and then 0.25 plus 0.6 times 0.6 is 0.61. Okay, yeah, that's good. So this is our cost right now, and of course we want our cost to go to 0, because when it's at 0 it means these are giving us exactly the values we want. So for example, if we wanted this to be 0, this value would have to be 1, this would have to be 0, which is going to give us the exact values which we're looking for, and that is how we get our cost value. So what we're basically trying to do when we make the network learn is we want to reduce this to 0. We want to make that 0. So there's actually a number of ways we can do this. There's the most popular method is called backpropagation, and I'm not going to be talking too much about that in this series because it's a bit complicated, but once you understand the finite gradient method, which I'll explain now, once you understand that, then you should be able to understand backpropagation pretty easily. So let's just create a bit of space down here and I'll explain what I mean. Now obviously, since cost is just a function, let's say we want cost, and all it's doing is really taking in all of this network's parameters, basically just the weights and the biases like this, which I haven't actually created, but I'll just create one now. Cost, so it's going to take all of those in and it's going to give us an output. In this case it's going to be 0.61. So what we can do is we can actually look at an individual weight and see its effect on the cost as a whole. So I just draw out a quick graph here, and then we'll go back here. We're looking at this weight's impact on the overall cost function, and it might look something like this. If you recall from the original overview video, I drew a graph similar like this, and I explained this, but basically what we're doing is this weight, so for example if the weight's value was 5, then its cost would be I don't know what this, let's just say this is like 0.3 or something. This isn't the actual cost because the cost is a sum of all of these other ones, but this is its individual impact on the cost. So we want to make this weight's impact on the cost as low as it can get. Now ideally that would be at this point. As you see the graph, this is the lowest point, so the cost is going to be lowest here, but that's a bit difficult to do, so we go for a local minimum, which in this case it's going to be around here somewhere. Now to do that, if we look on this graph, this is actually a curve, and if you know a bit of maths you should know that you can actually find the gradient of a curve by using calculus, but an easier way is to do the finite gradient, which is simply to look at what is here, look at what is like here. Let's say this value is like 5.000001, something like that, and gradient is rise over step, so you see how much the curve has risen over this 0.0001, I believe, and that will give you the gradient, which is probably going to look something like this. If I can draw a straight line, yeah, something like that. That's meant to be a straight line. Now if we look at this gradient, you can see it's actually telling us that the direction to go downwards. So this is going to be a positive gradient, and since it's positive we know it's going to be facing like this. If it was a negative gradient, for example at this point, then it would be facing like this. So what these tell us is we need to adjust the weight to go this way to reduce its cost, or if it was a negative gradient we have to go this way. So now what we can do using this gradient information, we simply move this weight to the left if it's positive. If it's negative, then we move it to the right, and what that does is you can see it's going to slowly move it closer and closer here till it reaches here, at which point the gradient's either going to be 0 or it's going to go this way and then come back there like that. So yeah, that's basically the overview of what we're doing. Now I just have to get into the technical aspects. So the first thing I'll do is actually create a cost function. We'll just say something like cost. This is in the network, so we're also going to have to pass in some data. So let's go down here, let's create a new interface for data. Let's just call it data point. And all we really need for a data point is the input variables or input values, so we'll just say inputs. It's an array of numbers, and we're looking for the expected output, like so. Okay, and then for the cost function, what we're going to do is going to take in some data. This is going to be an array of data points, and it's actually going to return single number, which is just the cost. So for this case it was 0.61. Now all we have to do to find the cost is we have to basically carry out this process multiple times and then find the average. So this 5.3 is going to be a single data point. So for point of data, or actually let me call this data set, so I can just call this data. And yeah, for data we're going to run it in the network, so if you do this dot run, and we're just going to, actually no, first I need to put the things as this, so I just copy this, we do this dot input layer. Oh, actually let's see what we're doing. Okay, yeah, so we're going to assume that the network already has its layer set up, so we'll just do input layer equals this dot layers 0, and then we'll do input layer dot neurons. Actually, we need to put it in, don't we? So we can look at the number of things here, and we're assuming the input layer has the same number of neurons as the data points input, so we can just do something like this: for const input of data dot inputs. And what I can actually do is get an iterable, so I can do this now: I input, and there should be a number. Right, hold on. Give me a sec, let me just check that this is how it should be. I should still be a number. Okay, yeah, okay. So now what I'm going to do is I'm going to set the inputs layers dot neurons I dot value is equal to input. Okay, so this is literally just putting the data into the network before it's going to run. Now we can run it, this dot run network, and now we just have to loop through the outputs. Oh, oops. Just have to loop through the outputs here and calculate the difference between that and the expected value and just square that. So let's just create sum equals 0 for const. We also have to find the output layer. Output layer equals this dot layers dot length minus 1 to get the last layer. Const neuron of this dot output layer dot neurons, and we're going to look for this. Actually, I'm just going to use an iterable neuron. Actually, why don't I just do it like this? This would probably be a better idea. Of expected output. We can find the difference, so actually let's find the neuron value equals this dot output layer dot neurons I dot value, neuron value subtracted by expected output. And we can actually do it the other way around, since that's how I've done it in the diagram. And then we do the difference squared. It's just going to be difference squared, obviously. Then we should add it to the sum. And finally, what I can do is I can divide this, so const average cost is equal to sum divided by data dot expected outputs dot length. That's going to give us our average cost for that one iteration. So let me just add that in, and now we'll create another variable called cost to count everything. Plus equals average cost for iteration. And once you've done that, we just have to total cost, right? And now we just have to repeat this, then find the average cost by dividing it by the number of data points inside the dataset. So average cost equals total cost divided by dataset.length. And if you think about it, you don't actually need to divide this, find the average cost of a single iteration, because it's not really going to change depending on if the dataset is bigger or smaller, because you're only comparing it against itself. But we can just do this anyway, so that it's a bit more simpler and it makes more sense in our own brain. So now we just return this average cost, just like this. Okay, so let's find the cost of our network at the moment. It's definitely not going to be 0.61 because I just made that number up, but let's just see what it looks like. So console.log this or network dot cost, and oh, I just realized we're gonna have to create some data. Alright, let's just create some data here while we're here. So const data equals data point, and the type of data I'm going to use for this easy, simple demonstration is going to be the XOR dataset. So if you don't know what a XOR gate is, it's like a simple binary logic gate, and basically I'll explain what it is. It only has 4 different types. So you input 2 values and they're either 0 or 1. So 0, 1, or 0, 0, that should be equal to 0. 0, 1 should be equal to 1. 1, 0, that should be equal to 1. But 1, 1 should be equal to 0. So these are our inputs. Now let's just create this in our data set. So we can do something like, we want something like inputs, and we're going to have 0, 0. Expected output is going to be 0. And I've just realized I'm also going to have to make this have a single layer now, because otherwise it's going to be a bit weird. So let me just delete everything from here, from the local storage. Right, and let me do this. We'll initialize some random weights, just like this. Right, and now I can do this. Oh, sorry. This is quite silly of me. Right, and now I can do this. Alright. Okay, let's just check we have everything in our local storage as we want it. Okay, that's good. And what I'm going to do is just create some more things like this. Expected output is 1, 1. So this is our data points, and now let's evaluate it over this thing, and we have a cost of 0.003. Okay, that's pretty good. So if we go to our storage, where we're storing all of our weights and biases, let's see what happens if we make this, let's say 1 or something. If you set that, you can see that had a slight effect on the cost. So well, now what we need to do is we want to actually find we want to loop through all of the weights and find their sort of corresponding graphs or corresponding changes which we need to make to them. So if we go to our network tab, or not tab, network class, we're actually going to create the learn function, which is going to do this for us. So what we're going to do, create some space again, and I'm just going to create learn like so. And what this is going to do is, all it's going to do is loop through all of these weights, check their impact on the cost, and then that's going to try and reduce its impact, or reduce as a cost for that specific weight. So we need to take in a data set to train it on. We'll probably just take in the same one, and we also have to type in a new variable called step size. So what this is if we find its gradient, once we found it, we need to know how much to go down by. So if it was a high step size, it would go down all the way there, so it would go somewhere over here. Low step size, it would go somewhere here, like so. So that's all it is. We could probably give it a step size of probably 1 to start off with, but yeah. So inside this learn dataset, I'm going to loop through all of our weights and biases. So let's just think about how we're going to do this. So for const key in this dot weights, and all I'm going to do is find first value of weight. So const, actually what I can do is just find the original cost, and we also want to do this for all of the points in the data set. So I'll do for const data of data set, just so it's looping through everything. The first part is going to be getting gradients of all weights in respect to the cost. So we'll do for const key in this dot weights, and inside this we have our weight currently, so we can actually get the initial cost. So this is a cost without anything to do with it. Initial cost is equal to this, and oh, I've just realized I've just realized the mistake I've been making. We shouldn't actually be looping through the dataset. We can just evaluate it using this dataset. You know, we don't actually have to do anything with that. So let's calculate the original cost. It's just going to be this dot cost, passing this dataset. Now we calculate the gradients of all the weights. So we do something like for key and weight const, and what I'm going to do is increase the value of this weight by 1, so const old weight equals const new weight is equal to this dot weights plus 0.001. Just want that to be a really small value. This dot weights key plus 0.001, and what we're doing here is the initial cost is represents of this value, this new weight represents this value. So what we're going to do is we have this new weight, we want to calculate new cost using this dot cost, and we just want to set this weight, this dot weights key is equal to new weight. Then we do this dot calculate cost again of dataset, and then once we've done that we can actually find the difference. So cost difference is equal to new cost minus initial cost. So we're going to find the cost at this point compared to the cost at that point, and then we also want to find the weight difference, and of course that's just going to be this number here. And then once we've done that, we can find the gradient by just doing rise over step. So the rise is the cost difference over the weight difference, which should give us the gradient at that point. And then of course we do have to reduce that back, so new weight minus this. And when dealing with calculus you usually call this number h, and it's when h tends to 0, but since we don't want to find a derivative at this point, we're just using h as a really small number. So const h is equal to that, and I'll just replace all of these with h. Okay, this is pretty good. Let's console that. Let's just output the gradients for now, just see what it looks like. So we have let's do network.learn XOR data. What's the error here? Oh yeah, no, let's just pass step size of 1. Okay, so this is pretty good. This first one is just going to be for the cost, so I can actually just add in. Right, so you can see we have the gradients in all of these. They actually vary, so the gradient for this one is actually quite large. So this has the biggest impact on the weight. Let's just find out which one that actually is, because then we can test changing it. We'll do console.log gradient, this dot weights key, and the gradient. So it is the negative 0.321. So if we go to our storage, look for that here, it's actually this one. If we change that by a lot, so let's just change it to we can just change it to 1 or something. We'll just change it to -1, and then reset, and we can see the cost actually decreased dramatically, which was quite surprising. So what was it before? It was like 0.33 or something, and now it's gone to 0.29, and now you can see its effect has gone down. So basically what's happened here is somewhere up here the gradient was really steep, we brought it down here, and now it's a lot less, which makes sense of course. So all we have to do is we got to check if this gradient is positive or negative, and then we also have to add this to the thing. So let's add weight vector key string change to weight, and this is going to be a number, and we want to do if gradient is positive, then we want to reduce the weights, so weight vectors key is equal to, what's this? Is the key a number? Oh, oops. This is not how I want to structure it. Actually, one sec. Let me just see up here. Oh, okay. Yeah. Okay. So yeah. So the key. This key is going to be equal to this, and we're going to make it a negative value, and we're going to make it actually the negative step size. So we'll just do -1 multiplied by step size, and then else if gradient is negative, we're just going to do the opposite. As you can see by our diagram here, if it's negative, we're going to increase it by the step size, so we can just set that to step size. Finally, we apply these weights. We just do something like for key in this dot weights plus equals weight vectors key. Okay, and let's finally find out final cost. Console.log initial cost, final cost. So we should be seeing some kind of increase. Oh, okay, that is definitely not an increase. Let me try and see what we're doing wrong. It could be that I've done it the wrong way round. -1. Okay, let's see what's going on now. Nope, that is still definitely an increase. I mean decrease. Okay, I think I might know what the issue is. We might be using a step size which is simply too high. So let me try and do something like 0.001. Okay, yeah, that's okay. There we go. Now we actually have a decrease. Yeah, okay. So this is good. Okay, so we actually have a decrease now, which is a good sign, because now it means that we're starting to get somewhere. Another issue you might be facing is because the gradients, I mean, we're not actually changing any of the biases, so I'll just do that now. It should be basically the same process. In fact, I might just be able to copy and paste this entire thing, or instead of copy and pasting, what I can do is I can just give it something. So weights, and this is going to be something containing the key and a number. And yeah, what I can do is wherever it says this dot weights, I can simply replace that with weights. And since we're basically doing the exact same process for the biases, I wouldn't want to repeat code. So if I just test it by passing in this first, okay, that's good. And if we pass in the biases, okay, yeah, so basically all I've done is, because we're doing the exact same code, we're just going to loop through the biases, reduce, find the gradient, and then do this. So if you imagine, instead of this being the curve of a weight with respect to the cost, if we look at this with the bias with respect to the cost, it's basically the exact same thing. So we could use the exact same code as well. All of this weight stuff might need to be renamed later on, but that can be done later. So yeah, now what I'm going to do is I'm going to see if we can change the step size, if that does anything. 0.88. So yeah, it's definitely making improvements, and now I can just test if this is actually going to change. We'll repeat this many times, maybe I'll do like 1,000 iterations. And instead of writing the initial cost here, actually I think we need the initial cost. I'll just take it here as well. Network.cost store data. Network.cost store data. Where's that already been written? Okay, we'll just say cost before, cost after, and yeah, let's just see how much of an improvement we can make. Cost before, cost after, just like that, and oh, okay, yeah, so you can see we're definitely making a lot of progress. I think I might have saved it in the wrong order because now it's gone and printed everything. Okay, yeah, so we went from 0.29 to 0.02, so this is actually quite good. And what I can do to demonstrate this is, let's just get all of these. So let's predict all of our values. So for example, we could do something like predicting 0, 0, and we'll do network dot layers 0 dot neurons 0 0. Value is equal to 0, and we would want to run this network. Let me just get rid of this, and now we also want to we'll just look at the results. So console.log json.parse json.stringify network. Let's just look at what we get before. So before we actually do any iteration, we get this as a result for 0, 0, 0.19 and 0.19, which is actually quite good. But then after, let's just do the same thing and after. So now we're going to get before, this is what it was before, and this is what it was after. So let's see, 0.19. To be honest, that actually doesn't look like it's changed much. Am I just doing something wrong or something? Let's see if there's a better improvements for 1 because 0.000 was already pretty good already. So let's look at 1. So before for 1 it was 0.57, which is like basically in the middle. That's definitely not what you want. And then if we look at what it is after, 0.39. So yeah, we're definitely making improvements. Now let's look at one of the middle cases. So 0, 1, 0, 1, and we'll reload that. So for the final layer, we're looking at 0.25, and then at the end we're looking at 0.96. So yeah, there we go. We can actually see big improvements here. So before it was 0.25, definitely not what we want, because if we look at this case, we want it to be closer to 1. So now as we've gone to 0.96, that's exactly what we want. And of course, I can just keep on continuing this. So if I go back to the console, get rid of all of this code. Actually, we could just comment it, get rid of it for now. Yeah, and then what I can do is I'm going to repeat it for maybe, we'll do 10,000, 0.002, and this is actually just going to keep on going. So I can just save this. So network.save weights biases, and now it's going to be an even better process. So let me do, oh, appears to have caused some kind of error. What is going on here? Okay, I have done something completely wrong. Okay, so let me just fix this real quick. We will initialize it with some random weights, like so. Okay, why are we still getting nulls? This is a bit confusing. I'm gonna just comment this line out. Okay, so we have this, and okay, and then let's save this. It appears my save network weight biases script wasn't working for some reason. Oh, okay. Is it working now? I can't actually tell. Let me see. Okay, so I think there's something wrong with this retrieve network biases, which is not ideal, of course, but I guess it's fine for now. We can fix that in a future part. But yeah, so you can see the improvements we're making. Yeah, so you can see the improvements we're making. We're going from a really high value 0.26 all the way down to 0.0005. So that's really good, and I'm really pleased with these kind of improvements. So yeah, that was a basic learning function. The reason why it's called the finite gradient method is because we're just finding the gradient at this point. In backpropagation, it's a very similar process, except we use a derivative to find a gradient, which is much faster because you don't have to run the cost function multiple times. But yeah, apart from that, this is really similar to backpropagation because it still uses gradient descent, the process of finding the gradient and then going to local minimum. So yeah, thanks for watching, and I know this was a very long part, but this is probably the most complicated part of a neural network, so it's good that we managed to get through it. Thanks for watching, and I'll see you guys in a future tutorial. Bye!